All right, good morning, everyone. Good morning. Great. I have lights. I can't really see any of you, but I want to hear you. Good. Cool. So thank you very much. I want to thank the organizers and the program committee for giving me this opportunity to talk to you. And I'm going to talk to you today about a project that we've been working on at Argonne National Laboratory in order to improve the future of C++ and to bring just-in-time compilation to high-performance computing in mainstream programming language. And I'm going to do this not really from the perspective of C++ in a programming language. I'm going to talk to you about the motivation and the project I've been working on and how it works and all of that. But I also want to talk to you about how I'm leveraging a whole bunch of different LLVM technologies in order to put all this together and make it work. And I want to try and explain to you how it works, and then we'll go from there. So where should I start? So the first place I should start, I suppose, is we're talking about just-in-time compilation. And let me talk a little bit about different reasons why people use just-in-time compilation, or at least 3 high-level reasons. The first high-level reason is because you can't do anything else. This is a good reason. Sometimes you have source code, you get it, and you're supposed to run it, and so you compile it just in time. Okay, that's kind of an obvious thing, but actually comes up in a lot of different contexts. And at the end of the talk, I'll talk a little bit about how we have an infrastructure to support this across a wide variety of use cases. The second high-level reason why you might want to use just-in-time compilation is to improve programmer productivity, or to avoid annoyed-looking programmers staring at their screen, because I do that sometimes. And sometimes this is a really important use case, because while you can compile things ahead of time in many cases, sometimes you just don't want to. There are a lot of things you can compile that you might not end up using at runtime, and it doesn't really make sense to compile them all when you use only a very small portion of the things that you compile. And the third reason why you might compile just in time is in order to adapt, to specialize the code during execution. And you can do this for performance, and you can also do this for non-performance related reasons. So for example, you may want to do adaptive sandboxing or other kinds of security or debugging related things to the code as you compile it. But for a moment, let me just talk about performance, because adaptive specialization is really important in many cases for performance. Okay, so here's, in some sense, the motivation that everyone here likely understands. For one thing, it's been true for a very long time that computers have been getting faster. This is very convenient. We know this quite well. But the other thing we know is that in recent years, serial clock rates have not really been going up. There are fundamental physics reasons for this. It's a really hard problem. We've been exploiting more parallelism, and that's been really important. But it's also true that you can make applications run faster both by improving the hardware and also by improving the application. And if you have adaptive specialization, you can often generate code at runtime specialized to a particular use case, to a particular configuration. And that code can run faster than generically compiled code. And if your clock rates aren't getting faster and you have to run your code faster, sometimes it's better just to make the code itself more efficient. Also on this slide, I have a diagram of a chip that is in an Apple phone. And highlighted here are lots of little boxes. And the little boxes all indicate different kinds of accelerators. And this is pretty cool, because there are a lot of little boxes. And that means there are a lot of accelerators. Now, some of these are fixed function accelerators, and some of them are GPUs, and some of them are other things. But the point is that modern hardware is actually quite heterogeneous. And when you are developing an application, you often run on hardware that is quite complicated, quite heterogeneous, quite multifaceted. And you might have to distribute an application not knowing exactly which hardware it's going to run on in this context. And you need some ability to specialize that. Because you're doing this for performance, you have to specialize this in a way that provides high performance. And this also often involves some kind of just-in-time compilation. for different kinds of hardware. Now, if I think about this in the HPC context, when I look at the ecosystem for large high-performance computing, large-scale high-performance computing, for supercomputers specifically, I notice a couple of things. One is that, on this diagram, you can see here there are various logos and pictures of different supercomputers, but underneath them are noted vendors providing different aspects of the hardware, perhaps the CPUs or the GPUs or other accelerators that go along with them. And essentially, on the high end, all of these machines have accelerators, GPU accelerators in this case. And we need to be able to target these, again, with high efficiency. All right. The other thing which I think is really useful to appreciate is that just-in-time compilation is really all around us. I mean, most people think about just-in-time compilation as something that happens in their web browser, which is true. Also, they may think about it as something that happens for their GPU shaders, which is also true. But if you look across the spectrum of applications, there are a lot of JITs. And this is really important to understand, that more and more applications are moving towards using just-in-time compilation in order to get better performance. And this is true for graphics, it's true for HPC, it's true for machine learning, it's true in many other contexts. It's true for regular expression processing, for doing spam filtering, for all sorts of things. And so it's really becoming an increasingly ubiquitous technology and part of the ecosystem. But there's also a downside to this in some sense, which is that it's still a highly specialized technology. There are, if you compare the number of people who know how to create JITs to the number of good C++ programmers out there, for example, the number of people who know how to create high-performance JITs is a very small number compared to the number of good C++ programmers. It's even a smaller number, I suppose, compared to the number of mediocre C++ programmers. And so, we really want to kind of do something to help bring just-in-time compilation, to bring those performance benefits, bring other related benefits to programmers who are not really, who don't really have the background in order to create JITs using the current set of tools that we have available. Okay. So we have, I should say, I should say, when we think about creating high-performance JITs, we should think about what this actually means in practice today. Because, I say we want to make this easier, but I should start by saying, what does it look like now? Now, it is not true that creating a JIT in today's world necessarily means sitting down and knowing how to write a program that writes assembly instructions. Sometimes it means that. But for the most part, we have better tools for this now. And LLVM is a really important tool in this context. We have LLVM, we have wrappers around LLVM, we have libraries built on top of LLVM, and this is a really important part of the ecosystem. Now, LLVM is not the only such thing in this ecosystem. There are also other frameworks that do this. Some of these other frameworks have lower serial performance for generated code, but generate code more quickly. Other frameworks in this space are specialized for other particular use cases, and so on. But there's a lot of LLVM in this just-in-time compilation ecosystem. And I think that's really important. But it also, as we know, working with LLVM, speaks to, in some sense, the difficulty of writing some of these kinds of tools. Because if you're a programmer and you're trying to create code that's going to execute just in time, you still often have to think about this as creating instructions. Not assembly instructions, but say IR-level instructions. And you do this one instruction at a time, one control structure at a time. And you have to think about how all these things fit together. And this is often not really trivial. So we wanted to try and create a tool that would allow programmers who know how to program in C++ to create just-in-time compilation, to take advantage of just-in-time compilation, to sort of create their own just-in-time compilation engines, and take advantage of the performance and other benefits that brings. And we essentially had three high-level requirements that we wanted to address. The first was that it should be as natural as possible to use in the context of C++. It should integrate well with the language. The second high-level requirement that we had was that the system should be usable across a wide variety of deployment targets. And this meant that we had one particular kind of requirement that came out of this, among many others, which was that the engine, the just-in-time compilation process, shouldn't access the file system during program execution in order to just-in-time compile the C++ code that's relevant. We couldn't have this for several reasons. So for one thing, on some targets, there really isn't a file system to speak of in this context. In other contexts, so for instance, on our large-scale HPC systems, there certainly is a file system. It's a large distributed shared file system, and it really doesn't like having a whole bunch of processes accessing a whole bunch of little files all at the same time. So it really is important to consolidate all of that metadata somehow into the executable so that that's the only thing that needs to be accessed. That can be loaded into memory, and we can avoid file system access at runtime. And the last requirement, and this is especially important in the context of C++, is that the process had to be as incremental as possible. We could not afford to have a compiler that essentially reprocessed entire translation units just to add little bits of just-in-time compiled code to the running process. That would not have scaled. It would not have been acceptable. One of the major motivations for this was to avoid long compile times. But of course, increase program productivity to avoid long compile times during ahead-of-time compilation. But that means that you're moving the compile time cost to runtime. So if you have a quadratically scaling compile time cost at runtime, that's also bad. And that had to be avoided. Okay. So let me also just quickly mention that what I'm going to show you is an implementation that is available on my GitHub page. This is something you can download and try out yourself. There's a wiki that gives you some instructions about how to install and how to use the thing. And please do try it out and provide me with feedback if you are curious. Okay. Oh, and the other thing I'll mention is if you're looking for a somewhat non-trivial example of how to use LLVM's or JIT infrastructure, at least sort of the old API, then feel free to check that out because it does that. Okay, good. So let me just show you what the interface looks like. So I said it had to be as natural as possible. This was our aim. And so here is the hello world for the C++ just-in-time compilation interface. You can see here that there is a function template. And the function template, well, it prints hello world, I suppose. But the important part is that it's a template, and it has this special ClangJIT attribute on it. And then if you look down below that, there's a main function. And the main function instantiates this function template and calls it. And that doesn't look all that weird, except for the fact that if you look at the template argument list, you'll see that that integer variable a, which comes from the command line, is being passed as a function template argument. That's not something you can normally do, as I'm sure you're aware. And so this is the hello world, but obviously there's a lot of infrastructure behind making that work. And the point of the just-in-time compilation project is, in fact, to make that work. Okay, so there's hello world. Here's a slightly more complicated example, but I wanted to demonstrate one other aspect of this, which is that sometimes what you want to specialize are non-type template parameters, some integer or what have you. And sometimes what you want to specialize are types. And here's an example where we have a function template, and what it does is it takes a type parameter and it prints out the size of the type. Okay, so that's not all that exciting, but if you look at the main function, you'll see that it takes a string from the command line and uses that to instantiate the type, and then runs it. Now, that's kind of ugly, I know. And I'll talk to you a little bit at the end about what we're doing to try and make this better. But I want to point out that this is an important use case and actually ties into a number of other use cases for C++ JITs, and we should talk about that as well. Okay. So here you can see as what I was demonstrating, and I just wanted to point out one thing here, aside from the fact that it works, and you can run this program, and you can put in types on the command line, and it will print out their size, kind of a convenient utility. But the other thing is, I want to point out the first two lines there print out the same type, f. And the thing I'm pointing out is that I spelled f in two different ways. This is one of the reasons why the strings are an ugly solution to printing out types, because you can spell them in multiple ways. And that's something that we want to address. Okay. So let me just give you a quick kind of technical definition of what this attribute does. So when you have the ClangJIT attribute, you can put it on function templates. You can't put it on classes and other things. You can just put it on function templates. And what that means is that the instantiation of the template does not happen during compile time, the regular ahead-of-time compile time, but will happen only later at runtime. The second property is if you have non-type template parameters, you can now put non-constant expressions into those as template arguments when you instantiate those templates. And those are used at runtime in order to instantiate the corresponding templates. If you have arrays, then those get turned into arrays with context-aware initializers, and this is important for a number of use cases. And then the third thing is that if you have a string, if you have a template argument that's a string, or that's a type, I should say, you can put in a string, and the string will be converted into a type and used in order to instantiate the template. Okay. I'll mention two kind of obvious limitations. So one is that the templates are not instantiated at compile time. They're instantiated at runtime. That means a compiler doesn't actually process the body of the template fully, and there are certain things that this interferes with. So for example, if you have the decal type auto on the template, for instance, and other type deduction mechanisms that rely on analyzing the body to figure out what the return type of the function is, that doesn't work if you're depending on a type that doesn't exist until runtime. The other thing is that since the specializations don't really exist at compile time, they're only created at runtime, you can't use the specializations themselves as non-type template parameters and do a bunch of other things kind of in that vein. All right. So I want to talk about the implementation here. I will mention that I gave a talk at CPPCon about this concept, where I talked more about the C++ implications of this. I gave some more examples of using this in C++, including a really neat example of using a compile time regular expression library at runtime to JIT a regular expression matcher. And if you're interested in that, then go check out the CPPCon talk. And also, there is a proposal to the C++ Standards Committee discussing this topic, and if you're interested in that, then go check that out. But I want to focus a little bit more on the implementation aspects here, and then I'll show you a smaller set of examples. So what happens when you use the just-in-time compilation interface with this ClangJIT, which is this implementation that provides the JIT functionality in C++? So a couple of things. So one is, from the user's perspective, all you do is add attributes where you need them, and then you compile, and you provide this -fjit flag, and the rest happens magically. But what happens in reality is kind of three things. So one is that Clang processes all of the regular non-JIT related code as usual. None of that really changes. The second thing is that uses of the JITted function template instantiations are translated into runtime calls. So the runtime, of course, is going to return a pointer to the newly generated function. And so those uses translate into runtime calls that return those pointers after the, okay, so the other thing that has to happen, of course, is there's a whole bunch of metadata about the thing you're compiling that then has to get serialized into the object file so that it can be used at runtime in order to instantiate the templates. And then all of those things, of course, get put together into the final object file. Those get linked. When they get linked, there is a runtime library that is sort of built into the Clang libraries. And that runtime library provides all the logic for doing the runtime stuff, but it also, of course, provides the implementation of this ClangJIT runtime call that has been substituted for uses of the function templates. Now, I mentioned that there's a bunch of metadata that has to get saved into the object file. So let me talk a little about what that actually is. So there are essentially 4 pieces that get saved for the regular compilation process. The first is that it saves a copy of the serialized AST, the abstract syntax tree, for the translation unit, and it saves that into the object file. I should note, by the way, that if there's no actual uses of the JIT in a particular translation unit, it doesn't actually save any of this. So it only saves it if you're using the feature in a particular translation unit. This is important, by the way, because Clang's AST is large, and some of the other things are actually not small either. And so you don't want to bloat the whole application for unnecessary reasons. So we save the AST. The AST to save the AST, I'm essentially reusing Clang's module infrastructure. So when Clang generates modules, it generates essentially a serialized AST. And for modules, it also has a really neat feature which is quite useful in this context, which is that it has the ability to save compressed versions of the source files into the serialized AST itself. This is obviously important. I remember I had this use case which said I didn't want to access the file system. One thing that I'll maybe touch on a little bit more later is that when you're compiling C++ code, sometimes it might not work, or you might get a warning, or other things like that. And when you get those things, Clang is really nice because it prints out little bits of your source code and points at things and stuff like that. And that's really convenient, but of course requires you to have the source code. So in this case, we use the ability of Clang in order to serialize the relevant source files compressed into the AST so that it can print those things out later. Okay. The second thing that has to be stored here are the compilation command line arguments that were used to compile the translation unit. This is important because at runtime, we essentially need to reconstitute the state of Clang so it can keep compiling stuff. And there are things like target flags and the like that affect code generation that need to be analyzed in order to reconstruct the relevant state of Clang. The third thing that gets saved is the optimized LLVM IR for the parts of the code that were compiled ahead of time. And this is important because, well, for 2 reasons. But mainly, it's to enable those functions that then are later used inside of the dynamically instantiated templates to be inlined as appropriate into those dynamically instantiated templates. You don't want to give up your ability to have inlining just because you're now compiling some stuff at runtime. And so we save the optimized LLVM IR so that things that need to be inlined later can be inlined later. And the other thing is that functions that are being dynamically instantiated might call other functions that are in your program. These might be external functions in your program, or they might be internal functions to the particular translation unit in which the dynamically instantiated template lived. Now, if you're calling external functions, then the JIT infrastructure already has a method for looking up symbols, and it's not so hard to hook that up. You can look up symbols inside your process and then link those into link those with the dynamically generated template instantiations. A little bit trickier for symbols that are not actually external, because those aren't exported. You can't, DL-sim them, essentially. And so what the implementation does is it goes through the translation unit, it looks for symbols that might be referenced by the templates, and it saves their addresses in a special table that the runtime library can then use in order to look those up. I'm not going to go in too much detail into the right-hand side of this diagram, but I will point out that the implementation also has support for Clang's CUDA implementation. So this allows you to dynamically specialize not only code that runs on CPU, but also for NVIDIA GPUs that are targeted by Clang's CUDA implementation, you can dynamically generate CUDA kernels. And in order to do that, we essentially have to take all the stuff that we save for the host compilation and save all of that for the device-side compilation too. And so it's all essentially the same, but it all lives in the object file so that at runtime we can read it, we can reconstitute the state of Clang, and let it keep compiling things. Okay. Now, so how does this really work in practice? So what we have here is a sort of diagram of the execution of the program. And so the program starts executing as usual. Nothing really changes. But at some point, the program might request one of these dynamically instantiated templates. And then it calls into the runtime library. And then a few things happen. So one thing is that there's a cache, and the implementation looks up in the cache to see if that particular instantiation has already been generated. If it has, it just returns the function pointer, and we're done. Okay, so now let's think about what happens when it doesn't find the instantiation in the cache. If this is the first time the runtime library has been called, it has to do that reconstitution of Clang state that I talked about. So it does that. Then what it does is it instantiates the new template. I'll explain a little bit more about how that happens in a minute. And that's added to the in-memory AST. Any code generation that requires is triggered. Again, I'll explain that a little bit more in a minute. And then that code that was generated, we then use LLVM's JIT infrastructure in order to link that code into the running process, to resolve any necessary symbols, and then to take the pointer to the resulting top-level function that was requested and return that to the program. The program then keeps executing, and so on. Now, there is a small technicality that I think is sort of worth mentioning in this context. So when you call into the runtime library, the runtime library has to know which template to instantiate and how to do that. Now, the arguments are provided to the function dynamically, but it has to understand how to make a correspondence between that template that was requested and the AST that was serialized. And it does this because the way that Clang processes templates is it has a representation of the template definition in the AST, and when you instantiate it, it essentially does a kind of copy and specialization of that. So here you can see that I have a very simple template, which doesn't really have a body, but if you look carefully, there's this thing that says compound statement that's empty, and that's the sort of body of the template. That doesn't get processed at compile time because it's a JIT template, but at runtime, the implementation essentially takes that part of the AST, it makes a copy of it, and substitutes in the types and non-type template parameters that are being used to instantiate the template. But when I call the runtime function, I somehow have to know which bit of the AST I need it to instantiate. And now you might think that you could store a pointer or something to part of the AST, and there are many implementation options here. But I found something that's pretty simple and works pretty well. So what I did was I had the implementation, as it's processing the templates ahead of time during regular compile time, it essentially has a counter. and it adds a number to each of the points of instantiation that call the runtime. And then when I call the runtime library, I just provide that number. And so these things get added to the AST, and then it can go through when it reconstitutes the state of Clang, it builds up a map that gives you an association between these instantiation point numbers and the relevant bit of the AST. This prevents me from having to store things like pointers directly into the serialized AST, and is a convenient way of doing that. All right. So how does this work? So when it goes to instantiate a template, the first thing it does is it looks up, using those numbers, the bit of the AST that represents the function template definition. It then constructs the relevant Clang data structure corresponding to the template arguments and substitutes those in. So essentially it calls the instantiate function definition part of Clang's SEMO. And then it retrieves the mangled name associated with that definition, because of course I have to co-generate it, and then I have to find the thing that I generated. So I need to know the mangled name that thing is going to correspond to. But luckily, Clang's cogen module has a nice function that's called getMangledName that I can use to get the mangled name. So it all works. But the other thing is that when I'm generating code, I generate the code for that function, but that is going to require other functions to be generated as well. I mean, most of the use cases for this are not really just to generate one function. The idea is that you're delaying instantiating a bunch of other templates that function itself uses in its body. And so what ends up happening is that when you generate code for that function, you then have a number of other functions that have to be generated as well. Now, Clang normally lazily co-generates these things as a matter of course. And so the implementation then iterates in order to generate all of the needed function definitions. And then it processes those and generates anything those need, and so on. And once that process is all finished, then we generate a new LLVM IR module. We then go through and adjust the linkage of all of the generated functions so they have external linkage, so we can use them later as necessary. We use the JIT infrastructure in order to add, to compile and then add that running module to the process. And then we take the IR that was generated, and we take all of those function definitions we just generated. In the IR, we change their linkage to externally available and kind of merge them into a running IR module. I'll show you what this means just now. So here's a quick example. We have here's a function. A use of the template. We start out with an IR module that just has the function we generated ahead of time marked externally available. We then want to generate the code for this template instantiation. So we do. And then we take the running module and link it into the new module so that those things that are externally available can now be inlined and such into the calls that we just generated. Then we generate the code, but we take the IR we generated and merge it back into the running module, marking everything as externally available, so that when we go to hit the next thing, we can link that module into the module for the new code again, do inlining as necessary, and so on. So let me just show you a few quick benchmarks. So this is a quick benchmark. It comes from the Eigen library. The Eigen library is a matrix mathematics library, and it's convenient for this kind of benchmark because it supports both dynamically sized matrices and statically sized matrices. And this is a benchmark that comes from the repository, essentially. I just marked it up to use the JIT. It does a computation. It's not really a useful computation particularly. It does a sort of iterative matrix computation. But I can show you the following thing. Here's the JIT version. It uses the version of the template library that's normally designed for statically sized matrices, but it uses it dynamically. OK. Let me talk first about compile time. So the compile time in some sense works as you might expect, in a sense. You can see here that so what I've done here is I subtracted the baseline. So I took the time that Clang takes to process the Eigen header files, essentially, off of the timing. And so here I have noted that the compile the version that uses JIT takes about a second. If you compile the generic ahead of time version, it takes about 2 3/4 seconds. And that's just for one data type. So if I decide to do all 3 floating point data types, for instance, it takes nearly 7 seconds. Now, how long does it take to instantiate the specialized version for particular sizes? Well, it depends on the size, actually. So if you take the trivial case where you have a 1x1 matrix, okay, that's sort of the baseline, it takes only 1/3 of a second. If you do 3x3, which is a real use case, it takes 2/3 of a second. 7x7 is 0.7 seconds. If you do 16x16, it takes 2 1/3 seconds. So you're almost back at the time that it took to do the generic ahead of time version, but the specialized versions run much faster. So here I have just a quick example. The 3x3 matrices, the specialized version essentially runs 8 times faster than the generic ahead of time version. For 7x7 matrices, it runs about 2.5 times faster. And for 16x16, there's very little difference. And if you think about it, this makes perfect sense, because the compiler can do a lot of unrolling and specialization for loops where it knows the trip count and the trip count is small. As the trip count gets large, then the difference between the code it generates for the known trip count and the code it generates for the unknown trip count actually gets more and more similar. And so the performance is more and more similar. I'll just quickly mention that the performance difference when you're running on the GPU is even larger. And that's because the GPU serial performance is more sensitive to a number of code optimization factors. One of which is that when you generate code for a GPU, you have to worry about 2 things. So one, in some sense, is the execution of the serial code. But the other thing is how many registers that code uses. Because when you run in parallel on a GPU, as you should, you need to worry about how many threads you can run. And the number of threads you can run is a factor of how many registers you're using within some limit. And so if you use fewer registers, you not only get better serial performance from specialized code, but you're using fewer registers, and so you can run more threads, and so your overall occupancy increases and your performance goes up. Okay, so that's quite important. Here I have the register usage. Skip time. So let me give you a quick example of how this actually comes up in practice. I don't have time for many examples, but here's one quick example. So this is an extract from one of the scientific simulation applications that I work with. And you can see here that there is a table that has a bunch of function template instantiations in it. These things are called at runtime depending on what the relevant configuration is that the simulation has to deal with. And the thing at the very bottom is an unordered map lookup that lets you pick the function instantiation that you want. So the actual kernel looks kind of like this. What we did was we replaced this implementation with the JIT version. And 2 things are true. So one is that the specialized code from the JITted version runs at high performance, like the ahead of time specialized version. The compile time is much better. And the other thing, which is nice, sort of a nice side effect, is that the overall performance of the application as you strong scale is actually slightly better with the JIT version. And the reason it's slightly better with JIT version is likely because the template instantiation cache that ClangJIT uses is based on LLVM dense map, which, as you may know, is a little bit faster than the standard unordered map implementation that the original code was using. So, nice side effect. Okay, just to give you some feeling about costs. It takes about 140 nanoseconds on an Intel Xeon in order to look up one of these precompiled template instantiations. If you try and create an instantiation using the strings as types, and it turns out only after you do some processing that you already have this instantiation, then that takes about 65 microseconds. And compiling a new template instantiation, well, it is C++. That's not super fast. So you're talking about a few milliseconds at least. But as we saw on the previous slide, if you have complicated C++ code, it still takes a long time. There are other concerns that I'll skip in the interest of time. But you do have to worry about ABIs, and you have to worry about how you process error messages and all those kinds of things. So the thing I wanted to kind of end with was, where do we go from here? So, as an LLVM project, we actually have a number of different LLVM users that need this kind of functionality. Like JITting C++ code is not really a new thing. It's not only used by this kind of project, which is focused on performance. It's used by the Clang project, for example, which is focused on providing an interactive C++ interpretation environment and execution environment. It's used by the LLDB debugger, right, in order to JIT functions that are otherwise inline and provide an ability to evaluate expressions and the like. So there are lots of different use cases for this kind of functionality that we can use and we can make available within LLVM. And my hope is that in the future, we'll be able to have a nice infrastructure to support these use cases in general. And so, the other thing I want to point out very quickly is that we've created this JIT functionality, and on top of that, our goal is to enable a kind of runtime auto-tuning on top of this, where we can have applications that dynamically adapt to their configurations and also to the hardware. And so we can compile instantiations, we can run them, we can measure their performance and other characteristics, we can adapt them, we can recompile, and so on. And I think in the context of current hardware trends, current software trends, in terms of trends for the implementation strategies for C++, this is going to become not only increasingly practical, but increasingly important. So with that, thank you very much.
All right, we have time for a few questions. There is a mic in the middle.
Hey, this is incredible. I didn't think the interface to a JIT could be as simple as a function attribute and compiler flag. That's awesome. I'm blown away by that. I have some questions about the fat object representation.
Sure.
So in order to have the serialized AST, that means you were able to run semantic analysis and report errors within my compile time code, with my to-be JITted code at compile time?
Yeah, so you can, it's just like with any other template in some sense that you haven't instantiated. So basic syntax errors and things related to non-dependent types and things, those all work the same way they did before. It's just the semantic analysis that's specific to the pieces you're putting in at runtime, that part has to have it at runtime.
Okay, and then you mentioned you have to save the kind of compiler or command line invocations. Sometimes I want tiered compilation of my JITted code, so I want JITted code quick, not necessarily highly optimized and slow. Is it possible for me to express JIT this as fast as possible for me, even though I compiled the rest of my C++ with O2?
Yeah, so that's a really good point, and is an important use case that isn't currently supported. There's a small complication, which is that sometimes things like your optimization level and what architecture you're supporting and things are actually exposed through the preprocessor when you preprocess the code. And since you're saving the AST, it's already been preprocessed, those decisions have already been made. But with that caveat, then it's definitely something we want to look at.
And then finally, can JITted code itself generate further JITted code and call into it?
So in the current implementation, no, but that's something that we want to add.
Awesome. Thank you so much. I think people really underestimate the power of runtime specialization, being able to beat ahead of time compilation.
Cool.
Very cool. Thanks.
Sorry, just one more quick question, please.
So you noted the similarities between Clang and LLDB. Can you talk about what prevented you from, let's say, using LLDB as a library to implement this feature?
That's a really good question. So the infrastructure, I think there are pieces of the infrastructure that we could share, and that's something that I'd really like to explore. It wasn't immediately obvious to me that the refactoring you would need to do to LLDB was much more invasive than the code I wrote to do the thing that I did.
Right.
But I think going forward, now that we have this prototype and we kind of understand more about what's going on, then I really want to explore how to have a common infrastructure here.
All right. Thank you.
Sure.
All right, thank you, everyone. Let's thank the speaker again.